Every database you have ever used is great at one thing: finding exact matches. Ask for the row where the name equals Smith, and it delivers instantly. But what if you want the items that mean something similar to this one, even when they share no words at all? A regular database has no idea how to answer that. Think of it as a search engine for meaning rather than for literal text. This is the question a vector database was built for, and it turns out to be the quiet engine behind semantic search, recommendations, and RAG. Let's dig in. First, let's see how this differs from the databases you already know. A keyword database matches literal values. It looks for rows where a field equals some text, or where a column contains an exact phrase. Fast and precise, but utterly blind to meaning. Search for car, and it will never surface a document that only ever says automobile, because the letters simply don't line up. A vector database asks a completely different question. It stores embeddings, high-dimensional vectors that capture meaning, and finds the ones nearest to your query vector. Now car and automobile sit close together in that space, so a single search finds both. You retrieve by similarity of meaning rather than by exact spelling. So how does a query actually work? Watch the path from stored data to results. First, everything you want to search gets embedded. Text, images, or audio each pass through an embedding model and become vectors. And those vectors are loaded into the database under a specialized index. This is the one-time setup that makes everything after it fast. When a query arrives, it goes through the very same embedding model and becomes a vector too. Now the question and every stored item live in one shared space, where closeness genuinely means similar meaning. Only then can we sensibly compare them. Here is where the index earns its keep. Rather than compare against every single vector, which would crawl over millions of them, the index jumps almost straight to the nearest matches using approximate nearest neighbor search. That is how you get answers in milliseconds instead of minutes. Finally, the database returns the most similar items, ranked by closeness. And you can filter as you go, asking for the nearest vectors where the category equals something specific, so meaning and plain metadata work together in one single query. Boil it down, and 3 ideas define a vector database. It stores embeddings and searches by similarity, not keywords. Instead of asking whether two things share the exact same words, it asks how close their meanings are, which is a far more powerful way to search messy, unstructured data. It leans on an approximate nearest neighbor index, so it stays fast at scale. Even across millions or billions of vectors, structures like HNSW find the near closest matches in a tiny fraction of the time a full scan would take. It is the memory layer behind modern AI. RAG, semantic search, recommendation, and deduplication all rest on it, and tools like Pinecone, Weaviate, Quadrant, Milvis, and Vector put into production. All right, let's lock in the essentials. A vector database stores embeddings and finds the ones closest to a query vector, letting you search by meaning instead of exact keywords. To stay fast over millions of vectors, it builds a specialized index for approximate nearest neighbor search, plus the usual inserts, updates, and metadata filtering. It is the memory layer of modern AI, making RAG, semantic search, and recommendation practical, with Pinecone, Weaviate, Quadrant, and Vector as common choices. Its key design choices are the distance metric, the index type, and how filtering meets the vector search. If the machinery behind AI search fascinates you, there's plenty more waiting over at standarity.com. Come explore with us.